Hello and welcome to our next lesson of the sine function. Today we are looking at properties of the sine graph as well as practicing how to actually graph the sine function using the measurements of different angles. And we're also going to make connections to real world situations that can be modeled using periodic functions, specifically the sinusoidal functions. So first consider this example where we have two students at an amusement park and they're riding two different Ferris wheels. And their motion on this Ferris wheel is, or their height as they're on the Ferris wheel is graphed using the following two graphs. So this is Ferris wheel 1, or A. This is Ferris wheel B. So first, what information about the Ferris wheels can you determine from each of these graphs? And as always, I suggest you take a moment and pause the video and try to see, based on the properties we discussed last time, what do you notice about each of these different functions and their graphs? So first, we notice that in both graphs, the period is 40 seconds. So as a general tip, when we're looking for the period, you can always look for two maximum points or two peaks and try to determine the distance between those. So looking here, this is a little bit past 10 and this is a little bit past 50, which makes the period about 40 seconds. And same with here, I can either look at these two peaks here, which goes from 10 to 50, so 40 seconds, or I can consider from here, from the starting point until I get to that point again, this is also 40 seconds, which means that one full cycle about each of the Ferris wheels takes 40 seconds. Now, in Ferris wheel A, the equation of the axis is h is equal to 7. So considering the maximum here is going to be 13 and the minimum is 1, then 13 plus 1 and taking the average, so dividing by 2, will give us h is equal to 7. And I will draw this for us here. So again, this is going to be a dashed line, or sorry, a dashed line. And it is h is equal, or h is equal to 7 because we're looking at height. And now I can also check that the distance from this equation to the maximum is the same as the equation from here to the minimum. And in the second graph, the equation of the axis, we again look at the maximum and the minimum. So the maximum here is 7, the minimum is 1. So 7 plus 1 divided by 2 is going to be 4. And the equation of the axis will be h is equal to 4. So what this means for us in terms of the problem is that in Ferris wheel A, the axle, which is the center of the Ferris wheel, is 7 meters off the ground, whereas the axle of Ferris wheel B is 4 meters off the ground. And already, which one do you think is the taller Ferris wheel between the two? And of course, it is Ferris wheel A, first because the axle is higher off the ground, but also that now we see the amplitudes are also different. The amplitude of Ferris wheel A is 7 because from this equation of the axis to the maximum, which was 13, we have 13 minus 7, which is 6. So here, again, I can do maybe, let me just copy this. If I consider this as the amplitude, then amplitude here is equal to 6, whereas the amplitude in Ferris wheel B is only going to be 3 here, which means that Ferris wheel A goes 13 meters up high, and again, it goes 6 meters below its equation of the axis, whereas here, this is only 3 meters above the equation of the axis, or from its axle, so it has a radius of 3 for a total height of 7. So this is actually radius. So the amplitude is actually the radius of the Ferris wheel because, again, consider we have in this example a Ferris wheel as such. So then this axle in the middle, this is going to be 4 meters off the ground. And the radius, which is 3, means that we go up by 3 meters from here. So again, a total height of 7 meters off the ground. And so, for our next part, how can you compare the speed of the two Ferris wheels from the graph? So, as mentioned in the first part, we do have that the period is 40 seconds, and the period corresponds to one complete cycle of the Ferris wheel, which means how long it takes for the Ferris wheel to go one full turn around the whole circle. So, we have to find that distance, which is the distance traveled, and divide it by the time that it takes to travel that distance. So one full turn of the Ferris wheel is equal to traveling the circumference of the Ferris wheel. So we calculate the circumference of each wheel based on the radius that we just found from the amplitude. So remember the circumference of a circle, the formula is 2 pi r, where r is the radius. So this is the circumference of Ferris wheel A and the circumference of Ferris wheel B. So in Ferris wheel A, we have 2 pi RA, which is the radius of the Ferris wheel A. And so 2 pi times 6 is approximately 37.7 meters. In the second Ferris wheel, the circumference is 2 pi 3, which is approximately 18.8 meters. So one full turn about the first Ferris wheel is 37.7 meters, whereas the second Ferris wheel is 18.8 meters. And here's also a second confirmation that Ferris wheel B is a smaller Ferris wheel. So now we knew the period of both of these Ferris wheels is 40 seconds, which means one full cycle takes 40 seconds, or it takes 40 seconds to travel the complete circumference. So we calculate the speed by dividing distance by time. So in the first Ferris wheel, 37.7 divided by 4 is approximately 0.94 meters per second. And because this was meter and 40 was in seconds, that's why we end up with meter per second. We have to keep those same units. And in Ferris wheel B, we are going a shorter distance, almost half of the distance, and in the same amount of time. And of course, we can also see that our speed is 0.447 meters per second, and the speed is also approximately half the speed of this one as well. And now some questions for you to think about. How does changing the radius of the wheel affect the graph? So first, we go back here. Remember, the radius has to do with the amplitude. So as we saw here, a greater radius equals a greater amplitude, which means that we are stretching our function upward. Whereas a shorter amplitude, or shorter radius means that we are compressing our function vertically to make it shorter. Next, how does changing the height of the axle of the wheel affect the graph? So remember, the height of the axle has to do with the equation of the axis. And here we saw where the height was 7, our equation of the axis is translated upward, so it starts at a greater value, whereas here where the height of the axle was 4 meters, our equation of the axis is lower and closer to the x-axis. So this is now where that translation upwards takes place depending on the height of the axle. And finally, how does changing the speed affect the graph? So the speed will be dependent on two different things, either the distance, which is the circumference, or the time. So we can either, if we speed it up based on the same circumference, we are decreasing the period. So this same cycle will be done, for example, in 30 seconds, which means we are compressing our function horizontally for it to be narrower. But when we do that, the amplitude doesn't change, the equation of the axis doesn't change, just the period is changing. Or if we are again going that same circumference but over a longer period of time, then we are stretching out our function horizontally. Again, the amplitude and the equation of the axis do not change, so this height and this line here will stay the same, but again, we are stretching it out, so it may look something like this. And the same could be said for Ferris wheel A. Um, and we could also change the speed by changing the distance. So if we have a greater amplitude, which means our radius is greater, which means the circumference of the Ferris wheel is greater, as we can see exactly between these two examples. They have the same period, but because the circumference of Ferris wheel A is greater than the circumference of Ferris wheel B, we can clearly see that the shape here is greater than this shape here over that same time period of 40 seconds. So just some food for thought of connections between transformations of the graph and how they can connect to real life examples, specifically for Ferris wheels again, because we are going to be working with a lot of examples having to do with Ferris wheels. But I suggest you think about other examples that have periodic motions and how each of the period, the equation of the axis, and the amplitude can be interpreted in terms of the real world problem that you can think that can be graphed using a sinusoidal function. So remember, sinusoidal functions are any function that has to do with a transformation of the sine function, and these are used to solve problems involving circular or oscillating motions at a constant speed. We just saw one of the circular examples, which is a Ferris wheel that goes around, and oscillating motions are a motion that you are swinging back and forth. So, of course, a swing itself is an oscillating motion. You can also think of a pendulum that is from like a clock that starts from the middle and then it goes swings back and forth. That is also an oscillating motion, and it is at a constant speed, especially with for a clock because it has to do with the seconds. It does go at the same speed. And so with each of these examples, sinusoidal functions can be used to graph the motion as well as the function itself can be used to solve problems involving these examples. So now think about some other circular or oscillating motions and think about how these graphs can be related and interpreted in terms of your examples. Later, we are going to see more examples, so I won't spend too much time there for now, but now we're going to be looking at how we can actually graph sine functions. And for the sake of this lesson, we are going to go really detailed in terms of the points that we are evaluating, just to notice some patterns and make connections, but then I'm going to show you a more simple way, especially the more you get practice, you don't need all of these points to be graphing your sine functions. But take a moment right now, use your calculator and try to fill in these values and keep exact values, so no decimals. If you have a square root of 2 over 2, leave it a square root of 2 over 2. And I'll be back in a minute to show you all the answers. Got the following values and take a moment and check all of your answers, but you should have got all of these values if you were using a calculator. But now I want you to consider any patterns that you might notice, specifically because these two rows here are one cycle in the positive direction, and this is the one cycle going from 0 to negative 360 degrees, so in the negative direction. And also to compare between 30 degrees and negative 30 degrees, so any value and it's negative, if you notice any patterns there. And then I'm going to write down some generalizations for you. So first, we notice that with 0, 180, and 360 degrees, which are the x-intercepts, for all of these values, so again, 0, 1, negative 180, and negative 360, these will always be equal to 0. So any multiple of 180 degrees is going to be equal to 0. We can generalize this. We write sine of 180 degrees times n is equal to 0 for n in the set of integers. So consider when n is 1, we have 180 degrees. When n is equal to 0, we have 0 degrees. When n is 2, we have 360. When n is -2, we have negative 360 degrees. And all values of n in this case will result in a 0 here for us. And so we can consider this as the halfway point of our cycle. So we will always have an x-intercept there. Next is the relationship between any value of x and its negative. So here, 30 degrees and then negative 30 degrees. Here we have an output of half, but here this is negative half. Same with here, we can see all of these values are the same, but just the negative value. Same with this row here, when now we go downwards in the negatives, we have all of these as negative, but then their negative input has the same output but the negative. And this is also another generalization here, and we write sine of negative x is equal to negative of sine of x. So their absolute value will be the same, but it will just have a negative output when you have a negative input for your function there. And finally, we can make a generalization about the repeating values. So we can say that sine of x plus 360 degrees times n is going to be equal to just sine of x. Again, given that n is an integer, because we want the cycle, the whole cycle to repeat, which is why we need an integer. So one complete cycle or two or three complete cycles, or if we're going in the negative direction, negative of one cycle, and so on. So that's why we don't consider real numbers. We can't have half of the cycle because the rule will not hold. So to see this, consider a sine of 30 degrees. And if I have n as -1, then 30 degrees plus negative 360 degrees is going to be negative 330 degrees. And that's precisely what I see here, that this value is equal to this value. Or similarly, here 60 degrees, then 60 minus 360 degrees, where n is equal to -1 here, then I will have negative 300. And we can also see that these two values are the same. And again, the reason for this is because this is a periodic motion, which means that if I consider two cycles there as such, oh, that's a little wonky. Okay, something like that. Then I can see these values correspond to all of these values here, and this is a shift of 360 degrees to the left. But also, if I go 360 degrees to the right and I extend my cycle this way, then the same will hold. All of these values here are the same portion of the graph that's just being repeated. And again, this is just adding one cycle over or to the right, or in this case of negative integers, we are moving n cycles to the left. To use the table of values above to plot the points and try to graph our function. Now, for this first part, it is going to be a little bit redundant. I do want you to graph as many points as you can, but later on, you only will need 5 key points, and that will be your first point here, your maximum point, which will occur at 90 degrees, and your 180 degrees, which is halfway through your period. And maybe I'm going to do these with blue. And then your minimum point, which is at at 270 degrees. So, okay, so actually I ended up changing the grid here for you. So then you can graph it a little bit easier. So really we need this point, the maximum point, again, the halfway point, are The minimum will be here and the 360 there. So then we just connect these points. And so I'm really only showing you the 5 key points here for each cycle, but I do suggest you try to plot all the different points and you can use your calculator to approximate those values, the exact values that we found, and find the decimal value there. And you should get this shape. And again, working from this side now, we do have the cycle going in this way. So again, those same 5 key points here and connecting them, I have 2 cycles of my sine function from negative 360 degrees to 360 degrees. Now for your next problem, we are going to look at the cosine function as well, just to see what the graph will look like. It is not a requirement for this course, so I won't be asking you to do any problems with the cosine function, just to introduce you so you can make a comparison. So again, take a moment to fill in these values, and then we will be graphing this function as well. These values you should have gotten, and I want you to take a moment and analyze these values and compare the positive cycle to the negative cycle. And here you can see that these values actually are the same. And in fact, these values of the ratios that we found here are the same values that we found when we were working with the sine function, but they just appear for different different angles. And the reason for that is because these all connect back to a right triangle, right? So if we have a 30-degree angle here and a 60-degree angle here for a right triangle, then of course the sine of 30, which is the opposite over the hypotenuse, so sine of 30, which is going to be the opposite over hypotenuse, this is going to be the same as the cosine of 60 degrees, which is the adjacent to that angle and its hypotenuse, because the side length that's adjacent to the 60-degree angle is also opposite to the 30-degree angle. And that's also the connection between the sine function and the cosine function. Really, they go back to our right angle triangles and the basic trigonometric ratios that we saw in our very first lesson. So now we're also going to plot our key points here to draw the function of the cosine function, or the graph of the cosine function. And again, I will be showing you mainly the key points, but I do recommend you plot the other points as well. So here we had 0, 0, 90, 0, I'll do 180, 270, and then 360, which goes up here. And if we work backwards this way, and then we go up here. Okay, so now I'm going to connect these lines and consider now again properties of this graph, the period of one cycle, the amplitude, the equation of the axis, the maximum minimum, and also how it is similar or different from the sine function. So right away I can see this is actually a symmetrical function because every value on this side is the same on this side. And that's what we saw with the table of values as well. Cosine of 90 was equal to cosine of negative 90. And here the maximum, oh, this should just be, sorry, this is 1. The maximum is 1, which is the same as the sine function. The minimum is -1, which is the same. We have the equation of the axis, which is the same, and the amplitude is also 1. And in fact, this is the sine function right here, and it's only been shifted 90 degrees to the left, or you can think of it as it has been shifted this way, 270 degrees to the right. So that's also another connection between the graph of the sine function and the cosine function. So they're pretty much the same shape, just translated along our grid. And with regards to the symmetry as well, the sine and cosine function can be classified as even and odd functions. An even function is when it is a symmetrical function about the y-axis. So just like our cosine function, f of negative x is the same as f of x. So the cosine of negative 90 degrees is equal to cosine of 90 degrees. And that's why we have also symmetry. However, an odd function is when you are rotating your function about the origin and you can obtain symmetry through rotation, which is what we see with the sine function. So if I rotate the sine function, then I end up with the same graph, and that's also why f of negative x is equal to negative f of x, or sine of negative x is equal to negative sine of x. So that's also another way to classify sine and cosine functions. They can be even and odd functions. Now, for the last part of this lesson, I wanted to briefly introduce you to the unit circle, and I will attach another video for you if you're interested to learn more about the unit circle, but it is a way for us to interpret the primary trigonometric ratios. So this is our Cartesian grid with our quadrants 1, 2, 3, 4. And we have, of course, our x and y axis. So the unit circle is a circle of radius 1 that is drawn about the origin. And first, I want you to consider how, especially given this diagram that I have for you here, how can we use the unit circle to solve for the primary trig ratios given the values of theta between 0 to 360 degrees? And the reason we consider only those values is because we are looking at the circle and its interior angle, which is 360 degrees here. So again, you can also make comparisons between the values of theta for sine and cosine that we found in our table of values above. But consider this triangle here, and you can really draw any triangle that has one side length on the x-axis. And so any point I can pick here, then I will draw a line this way. And then this is my triangle here. And then I can also have this angle over here. And this is now another triangle that I can form. And so looking at this one here, where theta is this angle here, then because my hypotenuse is the radius of the circle, which is equal to 1, then the sine of theta is just equal to its opposite angle. So this side length here is sine of theta. And similarly, the adjacent side length is cosine of theta. So when we have this point xy here, given these two distances, then xy is really cosine of theta, sine of theta. So the x coordinate represents the cosine of theta, and the y coordinate, which is the distance that we go up, again, which is opposite to theta, is the y coordinate. Same with over here. The sine is the y here, and the cosine is going to be the x coordinate going this way. And of course, with respect to the quadrants, there are quadrants where all the x coordinates are positive and all the y coordinates are positive or negative. And so from that, we can also make conclusions about the sign of or the polarity, so whether it's positive or negative, of the x coordinates as well as the y coordinates. So of course we know that in quadrant 1 and 4, this coincides with the positive side of our x-axis. So any angle in these two coordinates will have a positive cosine. And of course, from our cosine graph as well, we know that the values between 0 to 90, as well as between 270 to 360, which coincides with these angles here, because this is 0 degrees, this is 90 degrees, this is 180 degree, this is 270 degrees, and this is finally also 360 degrees. So again, values between 0 to 90, and then between, oh, this is 270 to 360 have a positive cosine, and these values all have a negative x coordinate or a negative cosine. Similarly, for the sine or the y coordinate here, we know that any value between of theta between 0 to 180 has a positive sign or a positive y coordinate, and any value between 180 to 360 will have a negative sign or a negative y coordinate. And again, we can match that to our sine function here. Any degree between 0 to 180 is positive, whereas 180 to 360 is negative. And understanding this relationship can help us also understand why sine and cosine are periodic functions, because this circle will be repeating, and I can continue this on. So from 360, I can again continue add 90 degrees here to have 450, and then so on. And all of these values will keep repeating to make that periodic motion or periodic behavior. And so this is already mentioned, but again, try to put in your own words now and interpret it for yourself. So using the quadrants, when is sine of x positive and when is cosine of x positive? And that was it for our lesson on properties of sine function, and you also got to see the cosine function and compare the two. So make sure you complete the practice set to get practice with these properties. And our next lesson, we are looking at transformations of sine function and its graph. And as always, don't hesitate to reach out if you have any questions, and I'll see you all in our next class.